Hello, everyone. My name is Michał Stęchły. I work at PsiQuantum, and it's a pleasure to be here again. Thank you, Robert, for the invitation. And today, I would like to tell you a bit about Construct, our software platform we have announced recently. But for those who don't know who we are, PsiQuantum is a company working on building photonic fault-tolerant quantum computers. And our mission is, well, basically to build and deploy the world's first useful fault-tolerant quantum computer. And today, what I will be focusing on is the useful part. So I work on the applications department, and we are focusing on applications and algorithms. So the software is not about error correction, not about photonic simulation, not about hardware modeling, applications and algorithms. But before I get to tell you about Construct, I wanted to share something personal about my company, which is that PsiQuantum is actually a bit scary place to work at. And it's a unique organization, and there are a couple of reasons why it's sometimes intimidating. So the first one is what you see here on the screen is a wafer of barium titanide, BTO, and this is the material that we have identified is critical for building optical switches, which are part of our fault-tolerant setup. And the problem was that it wasn't really manufactured on wafers like that anywhere in the world. But we needed that. So what we did is we created the whole manufacturing process for producing wafers like that. And right now, it works. We are making components out of this. We are pioneers, and we are working at the forefront of quantum computing, and not just quantum computing, as you can see, sometimes material science, and as I think you all know, sometimes computer science and like other areas. So a couple of years ago, when I was just starting learning about quantum resource estimation and fault tolerance, I had the pleasure to work with Yuval Sanders from UTS. And we spent a lot of time talking, which was mostly Yuval answering my questions. At some point, I said, hey, Yuval, maybe we should talk with some experts on this topic. And I think that was something to do with the representations of algorithms, fault-tolerant algorithms for resource estimation. And Yuval said, yeah, great, but you are an expert on this topic. And I said, hey, I just started learning this a couple of months ago. We just spent hours talking about it. I'm no expert. Well, Michał, unfortunately, there is no one else who spent as much time thinking about this particular problem in the world as you and I, which makes you an expert. Being at the forefront, doing something for the first time in the history, having no one to ask what's the right way to go, this is scary. If you really think hard and carefully about what it takes to build a fault-tolerant quantum computer, you quickly realize it's a gargantuan effort. When I was part of the DARPA's quantum benchmarking program, during one of the meetings, Josh Mutis from Rigetti came up to the stage, and he said, in order to find the ground state energy of, I don't remember, like some molecule they were working on, we would need a Costco-sized quantum computer. A couple of people laughed. We thought it's a joke, but unfortunately, Josh was serious. He did the math. For those who don't know, Costco is like American supermarket. Think IKEA, but instead of furniture, it's just like huge packs of food, right? This is the scale we are talking about. And you think about the scale, it starts making sense that when we are talking about funding, the funding, it will cost billions of dollars to build something like that. And, well, writing software for the machine that costs billions of dollars is pretty scary. And this picture has been taken 3 weeks ago during what's called groundbreaking ceremony in Chicago, where what it means is basically that the building of our facility in Chicago has started. And while I don't have any public roadmap to share with you or the dates when we are trying to build it, I can assure you that you don't start building a facility like that if your plan is to have it operational 20 years from now. So think about the software you are writing, you were working on. and think whether you think it's good enough to be work within the billion-dollar facility we are working with. And I think the software I have is definitely not there yet. We're working hard to make it. But every single time I think about the timelines we have, about when the fault tolerance will actually come, I'm really scared. Like, this is really intimidating and makes me really motivated to get back to work and actually make it happen. So to sum it up, working at PsiQuantum is scary, challenging, intimidating, because we're trying to build a first-of-its-kind billion-dollar quantum supercomputer, and we are trying to do it really as soon as possible, and this is really happening. Like, the construction has started. But even if we achieve that and we do this, we have the machine, which is like amazing feat of engineering and science, it might actually still not be useful. And it might be just like huge, expensive science experiments. Because you need to build a bridge between quantum hardware and actually useful, real... Why stop full screening? Sorry. Oh, and useful applications, like real world-changing applications. And as many people have identified, the applications part is something that for fault-tolerant computers, we're not there yet. We have just a handful of ideas of very computationally expensive applications. Our team has spent a lot of time doing research on applications, and usually most of the projects follow this path. So, great. So first we start for algorithm down selection. So you need to identify what the problem is and what is the right algorithm to solve the problem. You read the literature, think about it, you do that. Then you need to actually take those papers, take those big boxes with U inside, or U dagger, and write it in code, algorithm instantiation. And then you actually take those boxes and you think, well, actually, for my resource estimate to be worth anything, I cannot just assume this is like an oracle. I need to break it down into smaller chunks, which I will be eventually able to cost out, execute, test, compilation. Then a couple of weeks to write code for resource estimation, and then optimization. So we get the numbers, we know where the bottlenecks are, we try to make the bottlenecks go away, reduce the resources, fix the bugs, and we are in the circle. So most of the projects, and this is not just us, this is, we talk with other groups. Usually applications projects were taking 2 years ago, like 6 to 12 months. And if you think, well, until end of 2030, we have 5 years. That's kind of the timeline we want to assume. If you're lucky, you might fit about 10 iterations of going through this process, learning, applying the learnings, and having better applications, better algorithms. Some of these are obviously dead ends. 10 iterations, I don't know, like, I'm working on software, I do 10 iterations of a prototype, every week, every 2 weeks. Like, this is not enough to really drive the progress that we need to get the resources small enough that we can run it on first-generation quantum computers. So that's why we have developed a bunch of tools that allowed us to drive those numbers, those timelines really, really down and be able to iterate much, much faster. An example of the project that we did this way is implementation of algorithm called DFTHC. It has been published by folks from Google and friends earlier this year. So this paper was published in February this year. For our team, it took 2 months from reading the paper to having a working implementation, and not just implementation, but we also, in the meantime, fixed some bugs, found errors, in the paper, adjusted it to the active volume, which is kind of the metric we use, and make some improvements. The active volume, for those who don't know, it's a resource we use for our resource estimations. It counts the number of logical blocks that you need to execute on the active volume architecture, as we call it. terrible oversimplification is, if you don't know it, think about like T-gates, Toffoli gates. This is what people count in resource estimation. It's like another resource like that. So after we actually so it took us 2 months to get the implementation, get the resource counts. And after that, we started doing more research. So we took the 57 problem instances that came out of DARPA quantum benchmarking program, and like if anyone is interested, they are all open source in this link. And each line, colored line here, is different problem instance. And we have multiple points because we checked what are the trade-offs, kind of space-size trade-offs for different hyperparameters. At the beginning of the project, of like working with this set, which I think was like July, generating this plot took 5 hours. And when I talked with Chris, one of the scientists working on that, he said that actually generating this plot right now takes 5 minutes because of the improvements that my friend Konrad made to the performance of our engine. So as you can see, the timescale is really shrinking with those research projects. We are able to crank out more results, analyze not just one instance, but like 57 of them. And that's amazing. But as proud as we are of these results, and like that hopefully will be, more details will be published sometimes next year, we cannot work on all the applications and solve all the problems ourselves. Like, come on. I don't think there is a single team in the world that's able to tackle that big of a challenge. So we need to work together as a community to develop new algorithms, to find new interesting applications. And we are at the stage in the development of the quantum computing where rising tide raises all boats. So that's why we wanted to introduce you to Construct, our platform, and hopefully this will help you drive the innovation that we need to build useful quantum computers. So Construct is a platform. It consists of several different tools, and we are focused, as I said, on finding applications, writing algorithms, doing resource estimation. This is the core of what Construct has. Why did we come up with yet another quantum platform? Well, the reason is that when we started working on some of the tools that we have here a couple of years ago, there were really no other tools that allowed us to do the research that we needed, and the research on fault-tolerant algorithms. Because there's a lot of tools for NISQ. The problem is that they're not really good for FTQC algorithms because the scale is different. We are talking about billions of operations. We're talking about several layers of abstractions in the algorithms we are designing. We don't really think about error at all in the context of fault-tolerant algorithms because we assume we have fault tolerance, so we don't need to think about error correction. This is given. And the applications we are working with are just kind of bigger and more serious. So I will show you now how Construct looks like and a couple of tools. We'll start from how do we work on the design, then show you our workbench, our SDK, in which we write most of the algorithms, and then also show Resource Analyzer, which really helps with queries. I have nowhere enough time to show you all the interesting features that we have developed. Really, there is so much more I'd love to share. If anything in the presentations catches your attention, please come talk to either me or anyone else from our team, and I'll be happy to walk you through examples in details, show you every line of code, explain what it does. Well, just don't have time to do that on stage. OK, so full screen. OK, as I mentioned, this is the FTHC. This is the algorithm coming from the paper that we have implemented. And as you can see, well, it's a nice little algorithm, right? Each of these boxes is something much bigger. If you are working on this, well, you need to actually refer to those boxes in like other places, which might be other figures in this paper or other figures in other papers because someone else has described it elsewhere. And it is a bit cumbersome to work with this kind of representation of those algorithms. That's why we have this tool. I will actually try to make it bigger. Yes, it works. And this is Circuit Designer. So this is basically a visual editor for circuits, where you can click around, you can decompose, like look at those circuits, depending on what you're exactly working on right now. You can focus either on like some gory details, or you can focus on the bigger picture. This is all editable, drag and drop. We can take this, put it here. Like put this here. You can change on which register this is controlled. As you can see, there are like some big, some dots happening here, like appearing here, etc. Our researchers really love it. It helps a lot with what we are doing. And for this presentation, what I want to focus on is, I think I broke something. Obviously, yeah, live demos. Oh, it's here, right? So I want to focus on one particular part, which is this data loader. Right. So we have, a couple of boxes with data, and I will show you the implementation of like this whole algorithm a bit later on the high level. But in order to showcase our SDK, I want to focus on one of the very important parts of this, which is loading classical data into quantum computer. Right? We are doing a lot of pre-processing for chemistry cases like this, and we need to load some of what we already calculated on a regular computer into a quantum computer. So what we can do is we can open PsiQDE. This is our kind of development environment. I will open the VS Code in here. And here I have a little notebook with a demo. Try to make it bigger. Please load. OK, so while it's loading, as we heard, Wi-Fi, I have local version if it doesn't work. No worries. So what we will do is we'll talk about, as I mentioned, a data loader. We are here. OK, so I'll just switch the boring imports. And this is what we are trying to implement. So let's start from the classical version. Like, we want to implement this logic on a quantum computer. If control is equal to 1, load data, element from the data. Data is an array, at index L to register psi, right? So this is how the circuit looks like. And this is coming from this paper from 2018. This is how you implement that on a quantum computer. Well, to be honest, the classical version is much more concise and nice. But what quantum circuit gives you for this is you can load all the data you want in superposition and do kind of processing on the superposition and not just single element. So what we have here, we have a control register. We have what we call index register. So this L, it encodes which element from that array we want to load. And we have target register called psi. So if we have 0 in the L register, we get in this case, and we apply some x0 operation, which loads the 0th element, right? If we have 1 encoded in this register, we load the first element from our table, and so on and so on. OK, so how does it look like in Workbench? There is a couple of steps. So first, we need to, do you see it well, or should I make it a bit bigger? It's good? Bigger? OK. Up. So we start from creating the QPU object. It's like basically a handler class for doing a lot of different things. We define qubit registers. So we have 3 registers, control, index, and target. As you can see, we're using not just qubits, but quantum variables, which makes it so much easier to work with those data types. So for example, the target register, because in the data, as you can see, we have some negative numbers. We just use qint to encode it. And Workbench automatically takes care of making sure which bit encodes sign, etc. We don't have to kind of deal with this type of low-level stuff. Then we have some array of data, arbitrarily chosen. And we want to set control to 1. well, we want the circuit to actually work, right? It is all depending on control equal 1. And then, for the purpose of this demonstration, I will set the index register to value 7. So we are loading the 7th element. We could do that in superposition, but then it's a bit more tricky to actually read out the result and see whether you got it right, for, I hope, obvious reasons. And then what we do is we apply those multi-target, multi-controlled XGate to encode the data. So we enumerate over the data set that we have, and this is the register that, so here we apply on the target register, we apply XGate, encoding data in variable D, and that's conditional on the index being equal to I and control being true. And then we print out the data, print out the results. So we compare the value in the target register and the item that we wanted to get. So if we draw it, here you see the circuit. OK, this was the part when zooming in didn't work that well. OK, right, so this is the circuit that we use. We see here expected -1, got -1. -1 is indeed the last element in this array. Right, so this is what we got. And the problem with this circuit is that you actually cannot run natively multi-controlled, multi-target operations on a quantum computer. You need to decompose it to something smaller. So if you look at the paper, you will see that you can do that and decompose the control structure into what we call like clean ladders. So how do you do that? Well, I hope some of you can guess. We can add some filter. We call it filter, but these are basically compilation passes. Clean ladder filter. Yeah, we could spend some time talking about those compilation passes, how they work, how they can reduce the resource counts, etc. But I hope each one of you have seen compilation passes in your life. You basically don't want to know how they work. You just want to make sure that they work. So I won't. OK, so if we run it, we will see, OK, we got something like that. We wanted something like this. We are good, right? Notation is obviously a little bit different, but this is what we wanted. But then if you read the paper, actually, a lot of those gates can be further reduced. For example, there are those pairs here. They cancel each other out. So maybe we don't need to apply those operations. We can make it more efficient. Obviously, we have another filter for that. So once we do this, we go with elbow reduction filter. Up. We run it, and we see this picture. And this looks actually quite similar to the previous picture. So something obviously went wrong. And if you are really careful about looking how they implemented that, you will realize that they use different endian encoding for the target register, for the index register. So what we would need to do to make it work, we'll need to flip all the bits in the index register to get into from little endian to big endian, or the other way around. Fortunately, using kind of familiar Python syntax, we can just go and revert this particular register, and voila, we wanted this. This looks much more similar to this picture, so that's great. Now, it's nice to write bespoke code, but actually it's even nicer if you can modularize it and make it reusable. And that's where the concept of kubricks come in. So kubricks are equivalents of like kind of quantum functions. I'll show you how it works. I have, just in case, prepared one of the kubricks. And if I put it here, OK. So what's going on is we define the kubrick. It's called Google Select Optimize because, well, it's select coming from Google's paper, and it's optimized version of that. And we want to compute it based on the index register, target register, controlled on the control register, and using the data provided. And if we run it, it does exactly the same thing as we've seen previously. Voila, right? We got the same circuit. So Kubriks are really a powerful tool if what you want to do is write bigger, bigger circuits and bigger algorithms. And for example, what you could do is you could define two data loaders, load this classical data to two registers, and then add together what you got. And we are doing it here. Now in superposition, we are not setting index register to anything specific. And similarly, we define the registers, we define the data, we define the what select Kubrick we want to use. And then we are using the Gidney other. There are many different implementations of others. If you want, you can use some other. But now when we run it, we can see I highlighted this higher level structure, so it's easier to see that this is loading the first set of data, loading the second set of data, and then having an other here. Okay, so this, just to remind what the scale is, what we have here is just one of the boxes of this whole algorithm, and we need to implement many, many of them. So now I will show you a feature that I personally really like, and I think it's just too cool not to show, which is symbolics. And because of the time limits, I will not explain in detail how this whole algorithm is implemented. Again, come to me during the break, I will be happy to show you more. But we have the implementation of the whole DFT-HC, right? So what we do is we do a bunch of imports, boring, and then we do data instantiation, we create registers, we create the Kubricks that we need, compute them, and extract QRVs. So how it looks like. Well, here we define all the symbolic variables. By symbolic, I mean we're not using actual numbers, we're using symbolic. It's running SymPy under the hood. I don't know whether I want it to run with 73 number of orbitals. I want n number of orbitals, right? And I can express that using Workbench. So we also have some helper classes because quickly, if you take a look at how many different registers here, it's good to group some of them together and have abstractions that allow you to keep track of that easier. So I load this, then I define the qubit registers. Then we are using some Kubricks. One is outer select, there is some alias sampling. A lot of actually heavy lifting is happening inside this DFT-HC outer prep. And LCU, and then we run it, and now what we get out of this? So what we get out of this is a dictionary of resources, which each resource is actually a symbolic expression. We can maybe render that in LaTeX. Okay, so this is a symbolic expression that's showing us what's the active volume of DFT-HC. You can look at it, you can scroll it to the right because this is just the beginning of that expression. I told you this algorithm it's a serious algorithm, right? The problem is this expression in itself might not look like it's very useful, but it enables us with two important features. So the first feature is that it allows blazing fast evaluation. We don't need to construct the whole circuit for every different set of parameters. We can just take those symbolic expressions and evaluate it on 10,000 different points, as I do here. So I fix some of the parameters and then evaluate it for the others in order to analyze what's the interplay between different hyperparameters of the algorithm. So if we plot out the result, we will see that we are getting something like that. We have lambda-val2 and batch, and you can see that there is some nonlinear behavior happening here and here, which might be something interesting that people want to really look into. Having point resource estimates is useful, but being able to create the whole landscapes of resource estimates for different parameters is even more useful. And then if we look at this is another tool. This is the resource analyzer. If we look at this, we can actually see where the bottlenecks of the algorithm are. So, we can click the more red, the more resources it takes. I think it's way too small for you to see, so hop. And we can see that outer select and SOS, term, block encoding, the inner select, this is taking a lot of resources. I'm getting there. So what we can do, we can hide some of the less important features, just the blocks that are really low cost. We can take a look. Okay, inner select is our main offender, like clearly. Well, we would like to know more about how it's implemented. We can get this symbolic expression. It's still not very helpful to understand what the hell is going on there. But we have tools to simplify those expressions and then see, oh, actually, we can make certain assumptions about this expression, like what is bigger than what, and simplify some expression, some of the functions, and then see that actually the scaling of this is in terms of n is like n squared plus n plus whatever. Leading term is n squared. Those tools enable us this type of analysis, which is pretty useful. And now, because I see Robert already walking there, I wanted to get to the last slide, which is, thank you very much for your attention. First, not yet. First, with my friend Konrad, we are writing weekly newsletter about quantum software engineering. So I would invite you to subscribe. Some of you already are and like it. Second, we are hiring. So please go to our website. Please, if you want to get an internship or a full-time role, come to our team, and we'll be happy to see whether you're a good fit. And most importantly, if you want to play with the tools I showed you, or even better, if you want to do some serious stuff and groundbreaking work with these tools, this is the QR code, this is the link. Fill in the form, and we'll be happy to give you access and see what amazing feats you can do with that. Thank you very much.
Thank you.